For years, Redstoners have faced an issue, working hard to overcome it in many ingenious ways. That being, of course, the very slow speed of Redstone. In real-life electronics, a logic gate activates in 1/1,000,000th of a second, which, if we compare it to a redstone torch or repeater in classical redstone, taking 2 game ticks or 100 milliseconds, is literally hundreds of billions of times faster. So, if you want to do anything more advanced, such as run a game on a Minecraft computer or even a language model, you are stuck with logic at a snail's pace. Some redstone computers measuring their clock speeds in seconds per cycle, not the other way around. See, for all of those epic showcase videos that these other Redstoners make, they use a mod that unlocks the tick rate and optimizes Redstone, allowing logic to be processed as fast as your real-life computer can handle it. But what if you didn't need a mod to achieve this? 4 blocks. That's all it took to entirely break every single rule Minecraft has. It was so versatile, in fact, that it was both a very tiny update suppressor and the key to something far greater. This arrangement of blocks was so insane, in fact, that the technical community attempted to hide it, knowing it would be patched. I was informed of it by Hamter, a member of the Kronos server, and for a very specific reason. It had been theorized that the trick that makes it all possible could be reused, not as an update suppressor, but as a logic gate, enabling infinite frequency logic. The only problem was, nobody had cracked a way to actually do this. Having been sent a screenshot of the setup, the first step, of course, was understanding it. It includes a trapdoor and 2 dust pieces. Flipping the trapdoor, we get this weird floating state, and the bottom dust gets redirected. The reason this happens is because the trapdoor does not actually send block updates. In short, it doesn't tell the dust that anything has changed. Slightly modifying this setup to power the bottom dust, it will still work. And in fact, something really interesting happens. In this state, let's say that the trapdoor is closed. The dust is comfortably on top of it. And then the dust gets redirected into it, which is supposed to power it, but it doesn't, because the trapdoor isn't updated. If we do update it, the trapdoor does open, of course not breaking the dust, but then the dust that is supposed to power it is redirected out of it, again unpowering it. Effectively, this circuit will, for every update that the trapdoor receives, flip its state. In classical redstone, we would call this a T flip-flop, but in this scenario, it's more of a transistor. Now, how this device was usually used was as an update suppressor by simply looping it into itself, making it create infinite updates when it's activated. In our situation, we will be avoiding this as much as possible, because looping means looping infinitely, and that obviously isn't very good for doing controlled, precise logic. Now, we have a T flip-flop, so you might think a NOT gate is very simple. Just send in an update whenever you want to flip the signal and have it always inverted. And yes, this would work, if not for one very tiny problem. If we try this with a rail, nothing happens. Or at least it looks like nothing happens. Because if we check with an observer, the observer does actually detect a change in the trapdoor. In reality, what's happening is that the rail is updating the trapdoor twice, instantly. Sending updates twice is an inherent feature of rails. And if we try it with a node block, it does flip the trapdoor, but node blocks are hardly a good wire. What we need is a circuit that will take a rail and reduce its output updates to make it connect to a T flip-flop. The solution to this problem ended up being simpler than anyone had thought. The setup goes as follows. We use a slanted rail that will update both the node block and the trapdoor. We must understand that while yes, rails do send 2 updates, they do it one at a time, and each is processed separately. The first update will come and it will trigger the trapdoor. The trapdoor is then flipped, which will unpower both of these node blocks. The second update will come and update the first node block, which will flip the trapdoor. Then that update will flip the trapdoor again. Altogether, this has performed 3 flips, and the node block at the back is no longer budded. Then, that update will propagate to the second node block, which will update the output rail. Altogether, this beautifully simple circuit gives us a NOT gate, and it allows us to OR 2 values together. For those of you that have worked with conventional computational redstone, you might know that a NOT gate and an OR gate are enough to do any logic. And while that is also true in our situation, we will first look at one extra circuit that will be very useful for us. If we arrange two rails in a way whereas they should be slanted, but they aren't, the way that the updates propagate will actually mean that the bottom rail can be powered, in which case the top rail should be powered, but it's not because the updates will not propagate. Effectively, when you update it, it will take up the value that is inputted into the bottom rail. This is effectively a data latch or a D-latch, which allows us to latch values and will be insanely useful. This does also work on the latest version. There is one more problem to tackle before we can make any logic with this, and that is the fact that at this speed there is no tick, so there is no actual time or delay that a circuit can have. Generally, this is very good for us because it allows a lot more speed. But there is one situation in which it's horrible. Let's take, for example, an XOR gate. In classical redstone, if you send 1 and 1 into an XOR gate, the result will be 0. But that is because the inputs are synchronized. In this case, as we've covered, that is physically impossible, so one of them has to come first. If that is true, and it is, that means that the XOR will first have to output 1 and then turn to 0 when the second input arrives. This is generally a problem with all logic gates, and we cannot avoid it or simply use the gates that do not have this problem. But what we can do is we can have a circuit that latches the output of these logic gates. In result, effectively what we get is a circuit that controls the latching of the whole device, whatever we're making. This is also very useful and incredible because it allows us to control the frequency, so we can simply update this circuit as many times as we want it to activate within a tick. Great, so we have everything we need for an actual circuit. Let's take a look at something more advanced, starting with logic gates. Over here we have an XOR gate, which effectively all it does is it converts one of these two node block setups to produce one update and update a trapdoor, which, as we said, can be used as a T flip-flop. You might think this doesn't work because what happens if you input two inputs? But, as we said, it is single-threaded, which means one update at a time is checked. So if we just input both, they cancel out. And of course, we can flip the output individually. Continuing, we have the OR gate, which is a little bit of a more advanced setup, and it uses a node block setup with two trapdoors to output onto this rail. This is also inputted into from behind, and it simply ORs these two values together. Continuing, we have the XNOR, which is just the XOR, but this bit here is flipped. Then we have the NAND, which is basically OR, but the two inputs are inverted. So if this is powered and this is powered, then that rail there gets unpowered. And the NOR, which is very similar, simply inverting the output over here of the OR. We also have the AND, which is basically the NAND with the two inputs, with the output inverted. Here we also have a very simple wire, which works by basically propagating the updates and powering itself while this rail updates the next segment. There are two more advanced circuits I have to show you, one being an adder and one being a circuit that produces an arbitrary amount of updates per tick and then counts those updates on a counter. Let's start with the adder, since it's a more conventional showcase of what you should be able to do with this logic. It's a very conventionally looking adder with two inputs for every bit and one output. We have a half adder composed of a NAND gate and an XOR gate, and that NAND is then inverted and we carry. This is connected between two of these half adders, and of course on top we have the latching circuit. The latching circuit is built in a way where it updates from the least significant bit onto the most significant bit because that is the order we have to carry signals in. It has these arms that branch out on top of the circuit, which update the many latches within and ensure that this whole circuit will only produce as many updates as is necessary. To add two numbers using this circuit, we input the two 8-bit numbers at the bottom and then click the latch. This will trigger the whole circuit in the exact order we want it to, and provide us our result within the same tick that it was triggered. And in fact, it can do this as many times as we want within the same tick, given that it has the right inputs. Moving on to the second circuit I have to show you, it's a bit different. It doesn't really have a latching circuit. In fact, it has a circuit that is composed of conventional redstone for it to trigger. The reasoning for this is because this circuit is intended to be the input for such a latch, and it will trigger things a certain amount of times. When I press this node block, it will effectively create the amount of updates equivalent to the binary number inputted below. It does this by creating powers of 2 of amounts of updates by using these update doublers at the top and starting an update chain at different distances. This could, for example, be used to trigger a CPU n amount of times in a tick, or literally any circuit using this logic. In this case, I've wired it up to a counter which will count that amount of updates just to prove that it does actually work at said frequency. The expected result is basically that we will see the lamps over here be copied to the state of these rails out here via counting. This is highly inefficient for data transfer, but it does prove the concept. The only other big thing I worked on was this CPU over here, which, I'll save you the breath, is not done and it doesn't work. But it does prove that bigger things are technically possible, and many parts of it do work. This was quite a while ago, so I've forgotten most of it, but a world download will be available in the description if someone wants to snoop around. But effectively, the idea was that you use one of those clocking circuits to enable a specific amount of triggers per tick, and you control the exact frequency, doing operations one by one. Thank you for watching, and if you have any questions, feel free to leave them in the comments or join my Discord server and ask there. Bye!